It's inconvenient to learn. All right, so first just a little bit of bookkeeping. Here's the two texts I'm going to be using for the course, with a little bit of supplementing that just comes from the internet in general, just basic known stuff. Now this is only relevant, obviously, if you're not trying to get credit for this course, you're not required to do any assignments. If you are trying to get credit for this course, is there anyone trying to get credit for this course? Let's start with that question. Okay, if you're trying to get credit for this course, here is what you're going to have to do. First, you're going to need to get this textbook. You only need it for the first week or two. You can check it out. Masada has like 26 copies of it. I'll upload all this online, by the way. I always upload my lectures to my YouTube page. I'll create a YouTube playlist called Algebra. I'll upload all the lectures there. Usually takes me 24 hours to get the lecture up, depending on how my upload speeds are doing. Anyways, Masada has like 26 copies of these. So you can just go check them out. The librarian there, she probably know what you were saying. If you went and asked her, hey, I'm looking for the geometry book that Donald Timpson checked out all the copies of a couple years ago. So you probably remember that incident. So you'll need this book, and you only need this book for chapter 2 in it. That's the chapter on logic, which is what we're going to cover today. Now, warning for trying to get credit for this course, if you add any hopes that this would be an easier way to get your algebra credit, that is definitely not the case. And you can ask students who've had me before if my classes are easier than other classes. They're not. You'll be required to do a lot. And so your first requirement come next week will be solve all the problems in chapter 2. If you get stuck on some, that's fine, move on, and I can help you with problems that you get stuck on come class time, so don't bang your head against the wall if there's one that you can't figure out. Just keep moving past it, solve as much as you can. But yeah, solve the problems for chapter 2. So if anyone who's not here ends up watching the lecture, they're wondering about homework, if you're trying to get credit, you need to do that. This textbook, on the other hand, is not as easy to come by. This is one where you're probably going to have to do a bit of Googling around. Now, last time I did look for it, I could find it on Amazon for like $7. So it's an old textbook, probably hard to find, probably have to check a few places to find the textbook. But once you do find it, it's so old. You'll notice both these books, 1960, 1966, that's what makes them so hard to find. But since it's so old, it'll probably also be relatively cheap. So hopefully nothing too expensive there. So you'll have to get that because obviously all your homework problems are going to be inside that textbook.
So are these credits bonus or makeup for your algebra class?
It's just an algebra credit. It doesn't have to necessarily be a makeup. You can use it as a makeup. You can just use it however you use math credit. But you can't take. I'll put this into the academy system as a college algebra course, so that's what we'll count as. Any other questions bookkeeping wise? I don't know. Don't really know what else we need to talk about. And then obviously, any of you who are just interested in the textbook in general, this is what I'll use for almost the entire class. I also have a couple things in there. So if you're interested, there's that, and there might be a few copies in the community as well. When I went through this textbook, I did it with Joanne Timpson. She's now married to Taylor Zitting, and Alice Nicole Hammond. I also think she got married, I don't remember too. But, so they might have copies. I don't know. You have a copy?
No, mine is yours. I brought it for you.
Oh, okay. So there might be another couple that I haven't thought about, people I haven't thought about, but it's a somewhat common one around here. I think my sister Susanna has a copy. She's not going to do this course. She might end up doing the course. We'll see. Anyways, so those are books. Give you a rough idea. We'll be doing propositional logic, but just give you a rough idea of what this course is going to look like. Quick outline. First, we're going to cover logic. Propositional logic is what we'll mainly focus on there. And then we're going to cover basically some axioms for the math that we're going to be doing. And then we'll jump into college algebra the way it's taught everywhere. So that's roughly what the outline will look like. This will take a week, maybe two. This will take a week, maybe two. Maybe between these two, we've got 3 weeks, and then we'll jump into this. And that's roughly what it will look like. Okay. Now, why start with logic? Why would I begin an algebra course with logic? Well, fundamentally, mathematics is just using logic. So what high level is logic? Logic high level is taking the completely unambiguous parts of language. When I communicate with you, when someone writes a math textbook, what's ultimately happening there? They're communicating a bunch of mathematical information to me. I'm learning from that book. There's a lot of communication going on there. And they need to communicate in a very precise manner. It needs to be almost perfect communication. There is no margin of error in mathematics. And so logic is like picking away the parts of language that are completely unambiguous. And once we pick those parts away and have a perfect understanding of what exactly they mean, we then use logic to construct mathematics. And all mathematics is constructed out of logic. All mathematics presupposes logic. You use logic to construct mathematics. And so logic is a natural place to start. So we'll use logic before we jump into propositional logic. Do a quick recap on just reasoning in general. What reasoning is, and then logic focuses on this part of reasoning. So what does it mean to reason? When someone asks why you think B, you say, I think B because of some other statement A. A is the reason that you believe B. Or when someone asks you why you did something, you give them your reason, your justification, your explanation. The reason you accept it as true, your reasoning. And there's three, talking from a high level, there's roughly 3 ways that we reason. 3 ways that we justify statements, justify our positions. And we classify those 3 types of reasoning. So the first type of reasoning is deductive reasoning. This is the type of reasoning that we're interested in. The only type of reasoning we're interested in math and logic is deductive reasoning. Deductive reasoning. How does deductive reasoning work? Deductive reasoning is the reasoning you apply to these 2 statements to come to this conclusion. If I tell you that all men are mortal, and I tell you that Socrates is a man, then what do you know? Then you know Socrates is mortal. Now what deductive reasoning says is if, big if these 2 are true, then this thing right here is true. Deductive reasoning does not say all men are mortal. Deductive reasoning does not say Socrates is a man. Deductive reasoning says if all men are mortal and if Socrates is a man, then Socrates is mortal. So it doesn't say this is true, it doesn't say this is true, it doesn't say this is true. What deductive reasoning says is true is it says these 2 statements imply this statement. The implication is true. That's the truth that we talk about in deductive reasoning. That's the type of truth that we talk about in mathematics. And that's true to the extent that you can understand anything is true. There's no more fundamental version of truth than that implies that is true. And notice how this statement does not even care about the particulars of this universe. It is no way contingent upon this universe. Logic is in no way contingent upon this universe. If it were, we'd call it physics, not logic. What do we mean by that? I mean, we can keep those there. I mean, you can know absolutely nothing about what men are. I can take men here and replace it with A. If I say all A are mortal and Socrates is an A, then you know that Socrates is mortal. Furthermore, if I get rid of this mortal and I replace it with B, and I tell you all A's are B, Socrates is an A, therefore Socrates is a B. It's still true. Furthermore, I can get rid of Socrates and say, put a C there. If I tell you all A are B, and C is a A, then you know C is a B. In other words, the truth of this statement is in no way contingent upon what we're using in the statement. It's the form of the statement that gives us its truth. It's no way contingent upon the facts of this universe. We can get rid of everything that makes reference to something in this universe, replace it with some arbitrary letter, and it's still as true as it ever was. That's deductive reasoning. Make sense? Okay, now inductive reasoning. Inductive reasoning is reasoning that we use in our foundations of science. Notice that Up here, we only said if these are true. We never said that they actually were true. Well, sometimes we want to come along and we want to confirm a statement like all men are mortal. We want to call that thing true. How do I come to the conclusion that a statement like all men are mortal is true? I follow a bunch of men around for their entire lives. And I watch, he eventually died, he eventually died, he eventually died. And every single person I follow throughout their lives eventually dies. Crazy. So now I make some massive assumption that all men eventually die. Right? I didn't prove all men eventually died. I just saw a ton of instances of it. Every time I followed a man long enough, he eventually died. No one made it past 200 years. And so I come to this assumption, all men are mortal. That's called inductive reasoning. You induce from a bunch of particular instances to some generalization. You see something happen a bunch of times, and you assume, you make some generalization that it will always be the case. This is how we get our foundations in science. When I let go of this, what's going to happen? It's going to fall. How do you know that? From your experience. You've seen a lot of things fall. You've never had someone let go of the truck and it just hovered in the air. That'd be pretty amazing. Right? But is it possible that I let go of this and it hovers in the air? Is that possible? Yeah. This has a metal coating. For all you know, I rigged up some magnet system in the ceiling that when I step on it, it applies just as much of a force on this thing as gravity applies on it. And so when I let go, it just hovers there. That's possible. Highly improbable, but still possible. It is not guaranteed that if I drop this, it will fall to the earth. It is guaranteed that if all men are mortal, and if Socrates is a man, then Socrates is immortal. It's impossible for this to be wrong. It is very possible for our reasoning down here, inductive reasoning, to be wrong. So down here, we now have to argue using probabilities. This is a surefire thing. Down here, now we have to resort to probabilities. We have to say it's very, very, very unlikely that if I drop this, it will stay in the air. Right? And then abductive reasoning is the inverse. Did I cover this? Yeah, I covered that. Okay. Now, abductive reasoning is like the inverse of inductive reasoning. Inductive reasoning, you see a bunch of particular instances and you generalize to some assumption. Right? Abductive reasoning, you're doing the reverse. You're taking a bunch of your generalizations to try and reconstruct a particular instance. So, give you an example. Fill dropper in. Okay. So let's say you and a friend are walking down the sidewalk and you notice that it's a really cloudy day. Right? And as you're walking, you feel a little speck of moisture on your hand. What's your conclusion? It's most likely raining a little bit, right? You've had that experience before, probably. Pretty common experience. Now that's where you're using abductive reasoning. You have your generalizations that you know, you're outside, it doesn't rain inside, right? You've never seen it rain inside. There's clouds, you've never seen it not rain without clouds. You're taking a bunch of generalizations and trying to explain a particular instance, right? Now, that definitely isn't the case that it's raining. You could be walking next to Bob, and maybe Bob sprays a little bit when he talks. Maybe he had a particularly hard pee, and he got you a little bit, right? Or maybe the wall you just went past, you didn't hear it, but there's sprinklers on right there, and the wind was blowing a little bit, and it took a little drop of the water and hit your hand. There's a lot of explanations. So this is even less precise reasoning than this is even less precise reasoning than this. In this class, here's what we're interested in. Any questions on any of those three? Okay. So, jumping now into propositional logic. Propositional logic, starting out our foundations, we start with statements. Now, I'm going to call it a statement because that's what the textbook I referred you to calls it a statement. Most people call it a proposition. So proposition, statement, exact same thing. And so when we call it propositional logic, it's because it's talking about these things. Propositions, namely statements. Same thing. With me so far? Okay. Now I told you we need to use imprecise language to get at the most precise language. We need to make language as precise as we possibly can. So we need a definition for what exactly we mean by a statement. So what do we mean by a statement? A statement is a sentence that is either true or false, but not both. Pretty clear what a statement is? So a statement is true or false, definitely not both. It's one or the other. Good? Okay.
How do you get a statement that's both?
You can't. Otherwise, it's not a statement. By definition,
A sentence that's not false.
a sentence that's both true and false, how would you define whether or not it's true or false? We need to get at our foundations. We're saying, here's the assumption we're making. Right?
Yeah.
I mean, I know what you're trying to do, and it kind of makes sense. You're saying, let's do an analysis on sentences and see when it makes sense to talk about a sentence that's both true and false. Which sounds like it makes sense when you just say it like that. But what you don't understand is what you're presupposing is, let's apply logic to sentences that don't fit into logic. So it's just an assumption. It's not something we prove. We don't say we went and looked at a bunch of sentences, and we found some that were this way, some that were this way, some that were some other way, and we're just going to pick out these ones. It's just some assumption. If it's a sentence that's either true or false but not both, it's a statement. Key part of logic. We're not too concerned about classifying whether something is or isn't a statement. We're just saying what you can do with statements and what you can't do with statements. Because in mathematics, all we're interested in is statements. Make sense? So your intuition would reject anyone calling a sentence both true or false. Because you're used to thinking logically. And it's hard for you to not think logically. It's a difficult thing to do. Okay. Now, notation that we'll probably use throughout this class, but very typical notation. Notation. We typically use Greek letters like alpha and beta to represent statements. So I'll say the statement alpha, and alpha is a stand-in for some statement, like the sky is blue. Make sense? So, just common notation. Okay, so which of the following are statements? Go back home. Is that a statement?
No.
2 times 2 equals 5. That's false, right? So it's not a statement. Oh, it is a statement because it's false. Because it's one and only one of those two values. Perfect. New York is a suburb of Los Angeles. No, it's not. So not a statement, right?
No, it's a statement.
Oh, still a statement. It's just a false statement. Okay. Thursday up tar paper. All right. Is it true? Is it false? Is it both? Is it neither? Not sure what to do with that one. Not a statement. Right? The silliness of speedily. Not a statement. I am the most beautiful girl in town. Definitely true. So it's a statement, right? Okay. X plus 2 equals 5. Okay, this one is a gotcha. It's not a statement. I know. It's not a statement because it's dependent upon what that X is. If that X were 5, then we can call it a statement. Once we plug in some number for that statement, it's not a statement. So this, I'm not sure if we'll ever get into these, but this is what we call a predicate. For those of you who have predicates before, the way we could turn that into a statement is we could either add a quantifier like this. There exists an X such that X plus 2 equals 5. That then turns into a statement, or we could add a for all. Remember, adding quantifiers turns propositions into statements. Or predicates, thank you. So for those of you who have had more logic, those of you where this is new to you, well, I just set up here shouldn't make any sense, which is fine. But the gotcha is, it depends on what that X is. And if it depends, then we can no longer call it a statement. Because what if that X is toothpaste? Then is it a statement? We don't really know what it's saying. It starts turning into nonsense. What if I replaced it with the silliness of speedily plus 2 is equal to 5? Right? So since it depends on that X value, it's not a statement. That one's kind of a gotcha. Okay. But for the most part, your intuition will guide you correctly as to what is and what is not a statement. Okay, so now we know what statements are, roughly speaking. We have a rough idea of what statements are. Well, now we can start taking statements and combining them together to get new statements. So we can construct new statements by combining existing statements. I can take New York is a suburb of Los Angeles. That was a statement, right? I can take I am the most beautiful girl in town. That's a statement. And then I can and them together. And so we created a new statement. The new statement being New York is a suburb of Los Angeles, and I am the most beautiful girl in town. We now combine two statements into one single statement. You with me? And we did it with that key word, and. That's the conjunction of two statements. So, definition now of a new word, our second definition. Our first one was statement, next one is conjunction. So, if alpha and beta are statements, in other words, they are true or false, we all know what they are. Up here I showed alpha as New York is a suburb of Los Angeles, and beta as I'm the most beautiful girl in town. But it doesn't matter what the statements are. As long as alpha and beta are statements, the statement alpha and beta, put together into one single statement, no quotation marks there, is called the conjunction of alpha and beta. Okay? Does that definition make perfect sense?
Yes, of course.
Okay. Now, for those of you who have been here before, why can we take issue with that definition?
What's the definition?
Conjunction, right here, this definition.
Because you have or?
No?
Or because you don't have or?
What would or have to do with anything?
Using or conjunction.
No, that's for disjunction.
Oh.
Conjunction's and.
Nothing
It's
that's
like
obvious to me.
when you determine whether the conjunction is true based on A and B.
Perfect. So I said here, I said if alpha and beta are statements, the statement alpha and beta, I just called that thing a statement. How do I know that alpha and beta together is a statement? How do I know? Is that thing always true or false? Is it always one and only one?
Yeah.
How do we know? How are we positive? We need to define what the truth values are when we AND them together. Okay. So be careful that when you come across a definition, it actually makes sense what it's doing. So it just really told you that that is a statement. We better be able to determine whether that thing's true or false. So when is alpha and beta, when is that whole statement true? When alpha is true and when beta is true. When both those statements are true, then both of them are true. And alpha and beta is true. Yeah, sometimes it's hard to talk about logic because we're so used to using logic. It's like you're using logic to describe itself. So let's draw what we call now a truth table to determine how we decide the truth or falsity of this statement. Now, when I draw this out, just notation, and you're going to have to get used to this notation. Notation doesn't go away. The way we write alpha and beta is alpha, and then that upside down V, beta. You'll get used to this notation because I use it a lot, but that's a symbol for and. So now I'm going to draw what we call truth table. How many of you have never seen a truth table? Never seen a truth table. Okay, wonderful. So we've got two statements that we're working with, alpha and beta, right? Well, three statements. We've got alpha, we've got beta, and then we've got alpha and beta. So we're working with the statement alpha, we're working with the statement beta, and then we need to work with the statement alpha and beta. You with me?
Yes.
Now, notice that with the statements alpha and beta, there's four possible combinations. Let me assign actual statements there, so that you can pictorial, so that you can, or not pictorially, but so that you can see with your eyes that there's four possible cases. So let's say alpha is Donnie's holding a red marker, and beta is Donnie's holding a purple marker. You with me so far? Now there's four possible combinations. I can be holding both markers, I can be holding just the red, I can be holding just the purple, and I can be holding neither. Those are the four possible combinations in this scenario. So anytime you have two statements, there's four possible combinations. Either both statements are true, which we represent like this. So that case is when Donnie's like this. Alpha's true, beta's true. That's a T there. It's supposed to be a T, in case it looks awful. Okay? Next case we could have is I hold the red marker, but not the purple. So alpha's true and beta's false. Next possible scenario I could have is I'm not holding the red, but I am holding the purple. You with me?
Mm-hmm.
And then the final case is I'm not holding the red and I'm not holding the purple. Those are all the possible combinations. So now, in each of those combinations, we got to figure out if we can determine if this statement is true or false. Because we said this is a statement, which means no matter what, we should be able to call it either true or false. Right? And if we come across one where we can't call it true or false, then we lied and that thing isn't a statement. You with me? Okay, so if alpha is true and beta is true, then alpha and beta is true. If we make I'm holding a red marker true and I'm holding a purple marker true, the statement Donnie's holding a red marker and Donnie's holding a purple marker is true. Okay, what about the next case? What if I'm holding a red marker and I'm not holding a purple marker? So I'm setting up this scenario right here, you see? Now I'll make the statement, tell me whether it's true or false. Donnie's holding a red marker and Donnie's holding a purple marker.
False.
False, right? Okay, so in this scenario, it was false. Again, if I'm just holding the purple, then it's
False.
false. And then if I'm holding neither, it's true, right?
Yeah.
If I'm holding neither, then the statement,
Oh,
Donnie's holding a...
false.
No, it's false. All right. Yeah, don't disagree with me. I'm a big fat liar. All right. So there we go. We just created our truth table. And so now we know how to assign a truth or false value to this thing based off the truth or false values to these things. And we know that these things have truth or false values because it was given that they are statements. If alpha and beta are statements, so I know that's true or false, I know that's true or false. And now no matter what combination of true or false those are, I now know how to call that thing true or false. Does that make sense? Sometimes it might sound so simple that you missed some of the details. Because again, we're using logic to describe logic. So anything fuzzy there? Probably just get more comfortable with it as we keep going. But feel free to ask questions at any time, obviously. We didn't really have that discussion. But let's briefly have that discussion. I don't need to re-go over this material. Going over this material does almost nothing for me. So if it's also doing almost nothing for you, you're now wasting both our times. So make sure it's doing something for you. Otherwise, you're wasting my time. The only reason I'm here is to help you learn the material. These three already know this stuff inside and backwards. So if you two have any questions, you need to ask. And don't let the fact that these guys aren't asking questions mean, oh, you should just be getting it. No, they've seen it 100 times. Emma doesn't even know how many times she's seen it. So make sure it makes sense. Because I've also taught so many times, it's hard for me to remember what was confusing. Because I'm too familiar with it now. So always ask questions if anything comes up, anything feels fuzzy. Okay, we did that. Okay, now what about other conjunctions? So you took an English class and you learned that there's a bunch of conjunctions. And one of the conjunctions you learned about was a word called but. So how do we interpret that word called but? Is there a logical operator for the word but when we develop logic? And the answer is no. Let me give you a sense of why not. Because I told you in logic, we only use completely unambiguous language. We call it univocal language. Has one and only one interpretation, and it can be interpreted. You can make it explicit exactly what it's saying. But does not fall in that category, even though it seems like a plainly simple word to you. Let me help your intuition. So I write, let's look at the conjunction of two statements. If I say, I love you and I love your brother, then you know exactly what this is saying. It's saying, I love you is true, and it's saying, I love your brother is true, right? Now let's look at the next statement. I love you, but I love your brother. Do these two statements say the exact same thing, or are they slightly different?
They're different.
They're different. They're different somehow, but it's somehow slightly different from and. And yet, think about this statement down here. If I say, I love you, but I love your brother, is it true that I love you? Is it true that I love your brother? And so, logically, this says everything that this says. It says both of these are true, but there's something subtle in the word but that we can't put into precise language what exactly it's saying. What exactly do we mean by that word but? We mean this is true and this is true, and yet there's something subtle, something extra. And we don't allow words like that into logic, because it's not precise. If you can't communicate to a computer, we don't want it. Make sense?
Yeah.
So, and we talk about, but we don't. And because is also kind of in that category.
Or isn't.
Is not.
Or is not in that category. Can or be used in logic.
Yes, we will use or in both its ways. But we only care about one. So we'll get to or, I think, next, actually. Nope. Now we'll have a discussion about logic that I already had a little bit. So I already said this exact statement, but we'll say it again. In logic, we are only interested in the univocal parts of language. The parts that are not open to interpretation. There's one and only one meaning. Not equivocal. It's the opposite of what you do in poetry. Right? So we want words that are very precise, and we don't even let you use the word but. We throw that out. No, you're playing too fast and loose. Can't use crazy words like but. Way too much room for interpretation there. And. Use and. Okay. Another point. Is that going too far off the beaten path? We'll go over it anyways. In terms of sentential connectives. Okay, that sounds like a big word, but saying something simple. What's a sentential connective? It's something you can add on to a sentence. Sentential connective. And was a sentential connective. We took two sentences and we anded them together. We connected two sentences with and.
What is sentential?
Relating to sentences.
Oh.
So if it's a sentential connective, it's a connective for sentences. Good?
So it's kind of a sentential connective is kind of like a conjunction.
Conjunction is a sentential connective. Not every sentential connective is a conjunction. It doesn't have to be combining two statements together. It can just be added on to the front of a statement, or added on to the back, or added on in the middle of the back. It's just add-ons to sentences. Okay, that still makes that the result is a sentence. Okay, in terms of sentential connectives, which is the things we're talking about right now, the terms or phrases you can connect statements, you can connect onto statements in meaningful ways. Okay, so in terms of sentential connectives, what are those? The terms or phrases you can connect onto, I meant to say sentences there, in meaningful ways. We are only interested in the ones that are truth functional. What do we mean by that? The truth or falsity of the resulting sentence can be completely determined from the truth or falsity of the component sentences. Now, I know that was a mouthful, so let's do some examples and go over that again, and I think you'll be good. So, example. Let alpha and beta be two statements. Which of the following now are truth functional connectives? Truth functional sentential connectives. That's what we're looking at. So I know that alpha is a statement. Notice that the entire statement then, Jack believes alpha, is also a sentence, right? If alpha were the sky's blue, then Jack believes the sky is blue. This is now a sentence. It's still meaningful. It still means something. Okay. But is Jack believes, is that a truth functional connective? If I tell you alpha is true, can you determine whether this whole thing's true? No. Notice that you could, on this one, come back and look at alpha and beta. If you knew that alpha was true and beta was true, could you tell me whether or not alpha and beta was true? Yes. If you knew that alpha is true, could you tell me that Jack believes alpha is true? No. So this is not truth functional. Okay, next one. It is not true that alpha. You with me? It is not true that alpha is some statement, like the sky is blue. It is not true that the sky is blue. It's a statement.
So can you prove that that's true or false?
Can you determine whether it's true or false if you know that alpha is true or false? If alpha is true, then it is not true that alpha is false. If alpha is true, then it is not true that alpha is false. If alpha is false, then it is not true that alpha is true. I might be mixing you up a little bit, so let me pick an alpha that's false. Alpha is going to be elephants weigh 1 gram. You know that that is false. So you know that it is not true that elephants weigh 1 gram is true. You were able to determine whether or not this was true simply by knowing whether or not alpha was true. That's what we mean by truth functional. All right, alpha and beta, we already went over that. It is probable that B. If I know that, or that beta. If I know that beta is true, do I know that it's probable that it's true? Try it this way. If I know that beta is false, do I know that it's probable that it's false? No. We don't know any probabilities involved. So this one, once again, is not truth functional. So we're interested in very precise language. We're interested in language that can be interpreted one and only one way, no subtleties involved, and is truth functional. We can determine the truth or falsity from knowing the component parts of the statements. You with me? So and is a great example of one that we're interested in. And it is not the case, it is not true that. Seems like we could also create something for that, right? And we will. We call that one not, and we'll get to it. Okay. So, I don't know if that was too much of a tangent, but try and make it clear what we use in logic. Okay. So now, negation. Sorry, my chalk is dying on me. I'm looking for a good piece. No. Slightly bigger. Okay, so now negation is. Did we skip disjunction? Oh, weird. How did I do that? Disjunction first, or. Okay, so definition of disjunction. If alpha and beta are statements, the statement alpha or beta is called the disjunction of alpha and beta. Right? Now, when is it true and when is it false? It is false if both alpha and beta are false. Otherwise, it's true. You with me? We'll set up the truth table. Really quick notation. Alpha or beta we write as alpha v beta. So and was an upside down v, or is just a regular v. Okay, so let's set this one up. Once again, we're only working with alpha and beta, right? Those are our two statements. And then we have alpha or beta. So how many possible combinations of scenarios do we have? 4. 4. 2 to the power 2. So we can have, possibly we can have this one true and this one false. We can have this one false and this one true. We can have this one true and this one true. And we can have this one false and this one false. Right, in a weird order, just in case. All right. So now let's make intuitive sense of what these are saying, and then see that matches up exactly what our definition said. Back to our markers. Alpha is Donnie's holding a red marker. Beta is Donnie's holding a purple marker. You with me? Okay. Donnie's holding a, set the scenario, this scenario. Donnie's holding a red marker, or Donnie's holding a purple marker. True. So this scenario was true. You with me?
Yeah.
Next one. Donnie's holding a red marker, or Donnie's holding a purple marker. True. True. Okay. Next scenario. Donnie's holding a red marker, or Donnie's holding a purple marker. True. Right? Are you holding a red or purple marker? Yeah.
Yeah.
True. Donnie's holding a red marker, or Donnie's holding a purple marker.
False.
False. Let's read our definition now one more time. Or when we said it was true, and I think you'll see it now. It is false if both alpha and beta are false. Otherwise, it's true. Make perfect sense now?
Yeah.
Wonderful. Okay. Now, no, in English, notice that logic isn't restricted to English. Logic existed way before English existed. Aristotle was the first one to put down the rules of logic. He spoke Greek. That was well before English was a thing. So in the English language, we unfortunately use the word or two different ways. So we use or, we call it the inclusive or and the exclusive or, and give you a sense of that. So inclusive or. I tell you to be in one of my classes, you must take physics or calculus to apply for my class. You with me so far? Now, is it okay if you took both physics and calculus? Can you still come to my class? Is that okay? Yeah. Now notice that you're at a restaurant ordering, and the waiter tells you that order comes with a side of salad or soup. Do you get to say, okay, I'll take the salad and soup? I'll take both? No. So in this case, the or did not include the both case. In this case, it did include the both case. When we use or in logic, we're talking about it this way. We are not talking about it this way. That's called the exclusive or. Now, the exclusive or is a perfectly fine or. It's also a truth functional or. And we can still use it in logic. It's just we don't use it as often in logic. We use or this way a lot. We occasionally use it this way. And so we do have a special symbol for that. If we mean it in the exclusive sense, then we write alpha x or beta. X to make you think the exclusive sense one. The one that doesn't include as many cases. This one includes the case where you can take both. This one doesn't. It excludes that case. So inclusive or includes more cases. This one excludes a case. So that's why the XOR, that's where that's coming from. So we say alpha X or beta, and the symbol for that is the same as the V, or is the same as the or, but just with a vertical line coming down it. In case you can't see because of how small it is, it looks like that. So that's the XOR symbol, and we won't use that again. But there's nothing wrong with it, it's perfectly fine. You could use it in logic, it's just, for the most part, people don't, because you don't really need it. Did I hit twice again? No, just once. Okay. Now, negation. So, if alpha is a statement, the statement alpha is false is called the negation of alpha. We also say not alpha as shorthand for alpha is false. Okay, let's write out the truth table for this one. So notice that this one only depends on alpha. Right? So I've got alpha, and then the other statement I'm interested in is not alpha. How do we write not alpha? We write it as that symbol, a minus sign with a drop down on the right hand side, alpha. So then we have not alpha. Alpha, not A. Alpha. Okay, so now if we just have alpha by itself, how many possible cases are there? Two. Alpha can either be true or alpha can be false. That's it. Right? And if alpha is true, not alpha is false. And if alpha is false, not alpha is true. Crucial, it's going to sound stupid obvious, but then it's going to be something that you get stuck on a lot. Stupid obvious statement. Notice that it is always the case that either alpha or not alpha is true. One of them is always and forever true. One of them is always and forever false. If you know that alpha is true, you know that not alpha is false. And vice versa. Now it sounds stupid obvious, right? But negation is actually one of the hardest one of these things to wrap your head around all the way, believe it or not. I know, why, right? People must not be very smart if they're getting stuck on this. So we'll go over it. So that's why I was noting here. If you have two statements where one of them is always guaranteed to be true and one of them is always guaranteed to be false, those statements are called contradicting statements. The statement, Donnie is standing and Donnie is not standing are contradicting statements. One of them has to be true, one of them has to be false. I don't know which is which. Right now I'm standing, so this one's true and this one's false. But no matter how you position me, it is always and forever true that either Donnie is standing or Donnie is not standing. One of those has to be true, one of those has to be false. They're contradicting statements. Probably overstressing the point, huh? Okay. So no, not alpha is a contradiction of alpha. We always know that either alpha is true or not alpha is true. One of them has to be true. Oh, we're doing two things. Sorry. We always know that either alpha is true and not alpha is false, or that alpha is false and not alpha is true. We're guaranteed one of those two cases. Okay. Now that I've way overstressed it, let's use it. Which of the following are negations of all swans are white? You with me? We're negating all swans are white. If that's alpha, we're looking for not alpha. So the first one. Some swans are black. That's not alpha, right? This negates this. Right? If some swans are black, are all swans white?
No.
No. So do you see how these are negations of each other?
Yes.
You shouldn't, because they're not. Let me set up a world for you. Exactly. This negation will get you. Let's say that you live in a universe where half your swans are white and half your swans are black. Oh, sorry. No, let me set up a different universe. Let's say you live in a universe where all swans are yellow. Okay? So now we're in a universe where all swans are yellow. Is it true that all swans are white? Is it true that some swans are black? So these are not contradictions of each other. You always and forever, when you have contradicting statements, you always have to either have alpha is true or not alpha is true. No way around it. And so this is not the contradiction of this. Those are just called contrary statements. They're not contradicting statements. So if this is alpha, sorry, my thing looked up as I did my loop. This is definitely not alpha. It's something different. It's just another statement. Okay, now hopefully you're ready for this one. At least one swan is black. There we go. One of those has to be true, one of those has to be false, right? Still no. Okay, so it wasn't this one, it wasn't this one. I wouldn't give you 3 bad ones in a row, right? So this next one's got to be it. Or maybe I just saved it for the end. Who knows? Let's find out. All swans are white. Some swans are not white. Still playing with it? Let's think of a hypothetical universe. Let's go back to our universe of all yellow swans. You with me? Okay, we're in all yellow swan land. Are all swans white? No. Are some swans not white? Yeah, it seems to work. So if it's the case that not all your swans are white, that means that there are some swans that are not white. You see that? Furthermore, if some swans are not white, then it's definitely not the case that all swans are white. So if this one's true, this one's false. And if this one's true, this one's false. Guaranteed. These are contradictions of each other. If this is alpha, if we call this one alpha, then yes, right here we found not alpha. We found it. Now would I give you more than one not alpha? Let's find out. All swans are white, not all swans are white. Is that not alpha? That's a contradiction? Good. Hopefully that one's obvious. We just put the not word in front of it. This one was more tricky. And then finally, every swan is not white. Let's go back to yellow swan land. All swans are white is?
False.
False. So every swan is not white is?
False.
True, right? Let's look at it the other way. Well, we did in yellow swan land. So these are negations of each other, right?
Yeah.
No! Checking one example doesn't guarantee you that we got it. So let's set up another scenario. Let's say we live in a world where half our swans are white and half our swans are yellow. Is it true that all swans are white?
No.
No. Is it true that every swan is not white? Half of them were white. No. So false and false. So this one is not the negation. Yeah, you thought it would be easy, didn't you? I warned you. This negation one is one of the trickiest ones. It implies it's the trickiest, but this is the next trickiest. Okay. So hopefully you're getting a little bit of intuition with these negations, and you're learning how to not statements. So rather than just finding not statements, let's have you state not statements. So for each of these, I just want to know the negation of it. What's the negation of all men in Georgia are at least 6 feet tall?
Not all men in Georgia are at least 6 feet tall.
You can say not all men in Georgia are at least 6 feet tall, right? Try to say that another way without just putting a not in front of it. How else could you say it?
Some men in Georgia are not at least 6 feet tall.
Some men in Georgia are not at least 6 feet tall. Let's say that a better way. Are less than 6 feet tall. There's the negation without just throwing a not in front of it. It will always and forever be the case that either all men in Georgia are at least 6 feet tall, or some men in Georgia are less than 6 feet tall. Notice you don't need to know anything about men, you don't need to know anything about Georgia, you don't need to know anything about this universe for this to still be a true statement. For it to still be the case that either this one's true or this one's true. And either this one's false or this one's false. It has nothing to do with men in Georgia and 6 feet tall. It's just logic. All right, let's try the next one. All students in France like geometry.
Some students in France dislike geometry.
Some students in France don't like geometry. That makes sense? Let's do another one. Every rectangle is a square.
Not every rectangle is a square.
Not every rectangle is a square. Try saying it without just putting the not there, though.
Some rectangles are not squares.
Some rectangles are not squares. Go ahead.
If you said there exists a rectangle that's not squares, that's still negation.
Some and there exists are the same thing.
That's right.
Yeah, for those of you who know a little bit more logic, you're just distributing the not across the quantifier, right?
Yeah.
And turning it from a universal to an existential. Good.
Are you going over that with these guys today?
I don't know if we'll get to it today. That's why I thought it'd be more one day with logic. Okay, every circle has a center.
Some circles don't have a center.
Some circles don't have centers. For every pair of numbers, A and B, for every pair of numbers A and B, A plus B is equal to B plus A.
For every pair of numbers A and B, A plus B isn't equal to B plus A.
There exists a pair where that's the case. There exists a pair of numbers A and B such that A plus B is not equal to B plus A. Right? If it's not always the case, then that means that there is a case where it doesn't happen. Not always means there exists where not. Make sense? Okay, let's try another one. Some men play golf.
All men play.
No.
Don't play golf.
No men.
All men don't play golf. Or no men play golf. Both of those work.
Nice say.
There is at least one number x such that x plus 3 equals 7.
There is at least one number x such that x plus 3 is not equal to 7.
No, that is not the negation. Because you already know that that's the case. This would be true, and what you said would also be true. So how can we negate that? There is at least one number x such that x plus 3 equals 7. What's the negation of that? What does it mean to say, no, that's false? What are we saying?
X
There's-
equals 5.
We're saying what?
X equals 5.
We could say there's less than one number.
So there's no numbers.
Yeah.
Keep going.
So
There's no numbers x such that x plus 3 equals 7. So that's one way you can say it. You can say there is no number. There is no number x such that x plus 3 equals 7. You could have also said for all numbers, for all x, it is not the case. Not the case that x plus 3 equals 7. Oops. Common notation, you're going to see me do this 1,000 times. S dot T dot, shorthand for such that. Right, 100 times. So you see how both those are the negation? Okay, negating statements, it's tricky business.
Yeah.
It's not trivial. Make sure you got the right one. Think about it before you just move on. Okay, we did all those. Make sure I didn't do 2. Did that. Okay. Now that was just negating some statement. How are we going to negate like the conjunction of a statement? This is whole new level stuff. Okay, so now we're going to negate each conjunction. Today is Monday and the weather is cold. We're trying to negate that.
Today isn't Monday and the weather is not cold.
So there's our first shot at it. Let's look at that one. Today is not Monday and the weather is not cold. Okay, let's think about that one. And let's see if we can come up with a universe that makes us, that shows that these aren't contradictions. Jeez. Okay, so let's pretend that today is Monday, which it happens to be, and let's pretend that it's 100 degrees outside. Is this statement true?
No.
No.
Is this statement true?
No. Yeah, maybe.
No.
No!
Because it's Monday.
It's Monday!
No.
Ah, no. Okay, so that didn't work. How can we construct the negation of this thing?
Today is Monday and the weather's warm.
Today is Monday and the weather is warm. It's the same as not cold. If you think about warm and hot, it's the same thing.
Today is Tuesday and the weather is hot.
So we're looking at this one. Today is Tuesday and the weather's hot. We're going down a bad road here. Today is Tuesday and the weather is hot instead of not cold. Okay, let's look at that one. So, let's say today is Wednesday, and who cares about the weather? Is this statement true?
No.
Is this statement true? So it doesn't work in that universe. Your logic has to work independent of the universe. So that one doesn't work.
When we mess with today, I don't like saying.
All right, Jeremy, help him out.
Just
Change
change the answer.
the and to an or.
I was gonna change it to
Two.
You can't use that.
yeah, that's why I was gonna be wrong.
So, kind of want to do it with, sorry, we're going to do it with markers so you can see it. Well, maybe you can just see it. We'll see if you can just see it. So today is Monday and the weather is cold. Okay, someone makes that statement. Jack makes this statement and you're going to tell Jack that he's wrong. How do you show Jack that he's wrong? You either need to show him that this is false or you need to show him that this is false, right? And then he's wrong. So you need to show him that today is not Monday, or you need to show him that the weather is not cold. That's how you show he's wrong. That's how you make the statement false.
So you don't need to prove each of them wrong.
Well, just think for a second. If this statement is false, that means this statement's true, right? Is that appealing to your intuition? The way I show that this statement is false is to show that this piece is false or this piece is false.
So or negates and.
That's not the right way to say it. We'll give you the right way to say it here in a sec. The right way to say it is when you distribute not across an and, it produces an or. That's the way to say it. But for now, we'll just focus on making sure the intuition clicks here. So if you want this one to be false, you end up making this one true, right?
Yeah.
Now let's think about if we want this one to be false. So this one says today is not Monday or the weather's not cold. How do we make that one false? We have to make it Monday and we have to make the weather cold. That's the only way to make that false. So we have to state this statement. So if I want this to be false, I end up saying this. If I want this to be false, I end up saying this. They're negations of each other.
I see.
Make sense?
Yes.
Okay, so let's try another one. All cats are black, and all men are mortal.
No cats are black or no men are mortal.
Some cats are orange.
You already lost it. Let's take it one piece at a time. We want the not of all cats are black. What's that?
Some cats are orange.
Some cats are. What's the negation of all cats are black?
Some cats are not black.
Some cats are not black, right?
Yeah. Or some men are not mortal.
Or some men are not mortal. Perfect. Does that one make sense? Okay, let's go over the next one. Some rectangles are squares, and some triangles are equilateral.
Not all rectangles
Okay.
Let me
Well, what's the negation of some rectangles or squares?
No, really.
No rectangles or squares. Not some aren't. If some are, some still might not be. That's fine. It's no. The negation of some rectangles or squares is no rectangles or squares. Right?
No rectangles or squares, or no triangles are equal.
Perfect. You follow that? Next one. Some widgets are gadgets, and no wiggles are waggles. What's the negation of some widgets or gadgets?
No widgets or gadgets.
No widgets or gadgets, or
All wiggles are waggles. No.
some wiggles are waggles.
Why can't you say all? All wiggles are waggles.
On this one?
Yeah.
So you want to go from no wiggles or waggles to all wiggles or waggles, right?
Yeah, well, that
They can
contradicts.
prove you
So
wrong by
you say that one and all right here, all wiggles or waggles. Let's say you live in a universe where it's half and half. Okay. Good?
So no and some negate each other. Like they're kind of
All and some are very related. Yes. And we'll get to that, unfortunately, next week. Okay. So, what did we just do a bunch of demonstrations of? We just barely did a bunch of demonstrations of this rule right here. Now let's actually prove this rule. So I'm going to show to you that not alpha and beta gives you the exact same thing as not alpha or not beta. Let me show you that they're identical. They're logically equivalent. So the cases that we're looking at, we're going to talk about alpha and beta. Those are our component statements. We've got a not alpha in there. We've got a not beta in there. And then we've got a not alpha. We probably need an alpha and beta. Let's focus on just one statement at a time. First, we'll reconstruct this one and then that one. So alpha, beta, we'll do alpha and beta. Oops, that should be an alpha. Let's stop this for a second so that we can come over. And so that we're not just cramming on the side. Okay. So we're going to have alpha, we're going to have beta, we're going to have alpha and beta, we're going to have not alpha and beta, and then we're going to have a not alpha, we're going to have a not beta, and then we're going to have a not alpha or not beta. Okay. Looks like a lot, but it's really pretty simple. And we're going to have how many possible combinations?
4.
Just 4. Fundamentally, we're just using alpha and beta. There's only 4 combinations. These are just different combinations of alpha and beta. Okay, so our 4 combinations are, we can have alpha true, beta true. We can have alpha true, beta false. We can have alpha false, beta true. And then we can have both of them false, right? Okay, so if alpha is true and beta is true, alpha and beta is true. Should we fill across this way or down? We'll do down. We'll do one column at a time. Okay, if alpha is true and beta is false, alpha and beta is
false.
If alpha is false, beta is true, alpha and beta is
False.
if they're both false, then it's true, right?
False. No, false.
False. Okay.
Keep getting confused.
Okay, so now this column is just a negation of this column. We're taking alpha and beta and we're just noting it.
So inverse the reverse.
So
false, true, true, true.
false, true, true, true. Perfect. He just negated this column to get this column. Make sense? Okay. Not alpha is
False. False. True, true, true. False. True. False.
now we're ORing together these 2 columns.
Okay.
You see that? So false or false is
False. True.
False, true, false. Pick one.
It's false. It's false.
It's false,
Yeah.
right?
False.
Donnie's holding a red marker or Donnie's holding a purple marker.
Oh, yeah.
No. Okay. Yeah, think about concrete cases. Sometimes makes it fresh in the memory.
Yeah.
So false. Okay. False or true is?
True.
True or false is?
True.
But false is last.
True. It's still true.
All right. And true or true is?
True.
When they're both true.
True.
All right. Okay. Now notice, what were we trying to show you? I was trying to show you that this column is identical, the exact same thing as this column. They're logically equivalent. No matter what alpha and beta are, they spit out the exact same values. When alpha and beta are both true, this spits out false, this spits out false. When alpha is true and beta is false, this spits out true and this spits out true. When alpha is false, beta is true, spit out the same thing. When alpha is false, beta is false, they spit out the same thing. If no matter what, they spit out the same thing, if they always do the exact same thing, they're the same. They're logically equivalent. There's no difference between them. The same way that we say 3 plus 5 is really the same thing as 4 plus 4. It's two different ways of writing the exact same thing. This is two different ways of writing the exact same thing. Okay. Don't let all the fancy symbols throw you off. Okay, so now you can negate a conjunction. Can you negate a disjunction? Here's where it gets crazy. Negating a disjunction. All right, let's see if we can do this one. I will study hard or I will fail. How can we create the disjunction of that? I will study hard or I will fail. What's the contradiction of that? What's the opposite of that? If your teacher tells you, if your teacher tells you, you will study hard or you will fail, and you want your teacher to be wrong, what are you going to do?
You're not going to study hard, and you're going to pass.
And you're still going to pass, right?
Yeah.
So, the negation of this is, I will not study hard,
And I will pass.
and I will not fail. Or pass, same thing, right? Lots of ways we can say the same thing. So notice that you did the not of this, and you replace the or with an and. Almost the exact same thing as we were doing before, right?
Yeah.
So when you distribute a not across an or, it gives you not that and not that. Make sense?
Yeah.
Couple more examples. Some will work or all will starve. What's the negation of that?
Some won't work and all won't start.
No. Some will work. What's the negation of just that part? If I say,
All won't work.
there you go, all won't work. None will work is the negation of some will work. None will work and
None will starve.
Some will start.
some won't starve.
Oh.
Good?
Yeah.
Tricky, tricky. All right, next one. Every triangle is isosceles, or every triangle is right.
Some triangles are not isosceles, and some triangles are not right.
Perfect. No roses are red, or some violets are blue.
Some roses are not red, and all
No
violets. No.
And no violets are blue. No violets are blue. Two being negations. Okay. So, once again, we just barely did this. Now I think you need to see the truth table for this. It's almost identical to the previous one. You just flip your ors and ands. Okay, so these two things are logically equivalent. When you distribute a not across an or, it switches it to an and.
So if you distribute a not, then the symbol right there will change. Whether it's an and or an or, it will flip.
Right. So, this is the same as this, and not alpha and beta is the same thing as not alpha or not beta. Those were the two rules. Oops, I did B instead of beta, but I think you get it. Right? So that's how you distribute a not. Across a conjunction or a disjunction. Okay. Conversation about proofs. Because in mathematics, that is all you ever do is proofs, 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 proofs. Someone gives you some axioms, and then you just prove from there on out. Everything you ever did in math was a proof. That's all you ever did. No one told you that that's what you were doing. You didn't know when you were just doing basic algebra you were doing proofs. But that's all you ever do. It's just proofs. That's all we do in math. We also have some definitions along the way, but you don't really need definitions. Definition just takes a lot of words and puts it into one single word, right? So I could take that textbook right there, and I could do a find and replace, and everywhere it said statement, I could replace that with a sentence that has either true or false, but not both, and the textbook still makes perfect sense. Statement is just shorthand for saying a sentence that has either true or false, but not both. That's all definitions do. So in mathematics, all we have are definitions and theorems. Definitions just take a lot of words and reset it in smaller words, and then theorems are what actually add to the body of knowledge. Everything's just theorems. Everything's just proofs. That's how you extend a mathematical body of knowledge. So that's particularly why we're interested in logic, is proving things. So what does it mean when we're trying to prove something? Give you some basic high-level intuition. When we try to convince someone of the validity of some statement, when you're trying to convince your friend of something, you say, this is true because that is true, right? You justify this with some sort of that. And if your friend agrees that that is true, if your friend agrees with that, and they agree that that implies this, then they have to agree with this. All right? That's what we're trying to stress here. So now read this and hopefully it makes sense. This is a true statement because that is a true statement. If they agree that the that is true, and they agree that the this necessarily follows, then they will be convinced. And that's what proofs ultimately do. Logic can be summarized as a study of the rules for making correct statements, showing statements to be correct. It's probably a better way to say that. So proofs always consist of statements of the form, if so-and-so is true, then such and such must also be true. Every proof can be reworded, every theorem can be reworded, so it's stated in that form, that way. If something, then something else follows. Make sense? Okay, so let's do a quick example of a mathematical proof that you might have read before. If 3x is equal to 4, then what do you know? Then x is equal to 4/3. You divide both sides by 3 to solve for x, right? We're going to do a little bit of algebra when we're talking about logic, but don't worry, when we go back and start algebra, we'll start from the foundations. Just kind of using what you already know to help introduce you to proofs. Let's try another one. If a is equal to 2 and b is equal to 3, then you know that a squared plus ab is equal to what? You plug in 2 there. Can't hide a projector from you. Make it all funky so you can't read it. 2 squared is 4. Plus 2 times 3 is 6. So 4 plus 6 is? I don't know why you guys are even showing up for this class. In a sec. So all mathematical proofs are of the form, if alpha some statement, then beta some statement. That's always what's happening. Just verbiage. We call the alpha in these types of statements the antecedent or the condition, and we call the beta the conclusion. So when I say look at the antecedent of this statement right here, I'm saying look at 3x equals 4. That was the alpha part. The conclusion was x equals 4/3. The antecedent here was a equals 2 and b equals 3. The conclusion was a squared plus ab equals 10. Antecedent and conclusion, or condition and conclusion. I'll typically say antecedent and conclusion.
What about on your, this is true because that is true?
This is true because that is true is the same thing as if that is true, then this is true. Kind of. It's 2 and 1. It's not saying if, it's actually saying since. Since that is true, then this is true. You with me?
Yeah.
And then the way that we actually say that is, well, we can still call that an implication. That's fine. Since is what we mean when we say the antecedent is true. In mathematics, we don't ever actually say that the antecedent is true. Even with the axioms. You do not say the axioms are true. You say, if the axioms are true, then what else is true? That's the question you ask. So for example, we have what we call Euclidean geometry, which has Euclid's postulates. And then we have non-Euclidean geometry, which has other postulates. We do not say that these postulates are true, and we do not say that these postulates are true. We say that these postulates imply the Pythagorean theorem. And we say that these postulates imply some other theorem. That's what's true. Because these postulates actually contradict each other. They can't both be true. So in mathematics, we never say an assumption is true. We say if the assumption is true, then the conclusion is true. That's what's true. We don't say all men are mortal. We don't say Socrates is a man. We say if all men are mortal and if Socrates is a man, then Socrates is mortal. It's the implication that we're always saying is true. A subtle difference, but it's an important one to understand. That's why mathematics is infallible. Because it only focuses on the implications. Make sense? So this one drifts outside of mathematics with that word since. And the only way you can get a since word in there is when you get to science and you start inductively reasoning to a premise. Then you can start putting the since in there. You can say, since we have Newton's third law, da 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 da. And now it's contingent upon this universe in some way. And so you're making statements about this universe. Not statements that are true, even if this universe ceases to exist. Which is what math is interested in. Okay, good question. I think we covered everything on the slide, right? Any more questions on it? Okay. Did I only do it once? Sorry. Can't touch my keyboard because I'm all chalky. Okay. Implication now. Okay, this is the hardest one, but once you get this one, you're basically done with propositional logic. But this is the one that it'll make perfect sense, and then come next week, it won't make sense again. And it will have to be re-explained to you. Okay, implication. What's an implication? If alpha and beta are statements, then the statement alpha implies beta is called an implication. Good so far? Now we have a bunch of ways of saying that exact same thing. We also say, if alpha then beta, that says the same thing as alpha implies beta. We also say beta if alpha, that says the same thing as alpha implies beta. We also say alpha only if beta, that's the same thing as alpha implies beta. And we say alpha is a sufficient condition for beta, that also means alpha implies beta. And we also say beta is a necessary condition for alpha. That also means alpha implies beta. So there's a mouthful of terminology there, and we'll try to get comfortable with this terminology bit by bit. But they're all saying the exact same thing. Alpha implies beta, said 100 different ways, and those 100 different ways will come up in pretty much any textbook you use. Maybe not so much a necessary condition or insufficient. That one seems to die down. Anyways, notation. Alpha implies beta, how do we write it? We write it as alpha, arrow pointing over to beta. Alpha implies beta. If alpha, then beta is the way we typically read it. We don't typically say alpha implies beta. And it's the form that we give all theorems. Alpha implies beta. Okay, so let's get comfortable putting some statements in the form. This is the most standard form, if alpha, then beta. That's the most standard way we write it. Let's get comfortable making implications said this way rather than the way that they're written here. You with me? So let's try the first one. If I eat strawberries, I get hives. State that in an if alpha then beta form. If I eat strawberries, then I get hives. You just have to stick it that then in there. Okay, let's try the next one. People who don't study mathematics don't have good sense. If you don't study mathematics, then you don't have good sense, right? The crops will be saved if we have rain this week.
If we have a rain this week, then the crops will be saved.
Perfect. Notice that the antecedent came at the end on that one. If we have rain this week, then the crops will be saved. That was this one. If alpha then beta is the same thing as beta if alpha.
But you could say the crops will be saved if we have rain this week. Because beta if
That's what it says.
Let's see.
If,
Sorry, which one were we on? We were on this one.
Yeah.
The crops will be saved if we have rain this week.
if the crops
that
are
would be
saved,
proper
we have
implication
rain
form,
this
right?
week.
Because it's just another one of the.
If you try, I'm not sure what you said. If you reword that in an if-then statement, it's if we have rain this week, then the crops will be saved.
Yeah, I know it's not this form, but it is an implication form.
What did you say?
Just in different form. I said up there with the, we also say there's a beta if alpha. That is in a beta if alpha state form. That is an implication, right?
This one is in this form.
Yeah.
Yes, that's what we're pointing out.
Okay.
So we took it from this form and we rewrote it this way. We took what was at the end, moved it to the start,
Yeah.
and took what was at the start and moved it to the end. Yes. Good. It will rain tomorrow only if it gets cold.
If it gets cold, it will rain, then it will rain tomorrow.
If it will rain tomorrow, then it will be. Then it gets
Wait,
in
hang
it.
on.
If it will rain tomorrow.
Only
then
if it
then it
gets
gets cold. Then it gets cold.
So,
Only if it gets cold, then it will rain.
what are we agreed upon? State this in if-then form. If what? Which one's my antecedent?
It will rain tomorrow.
It will rain tomorrow is my antecedent? It's not saying if it gets cold, then it will rain tomorrow?
Oh,
It will rain tomorrow, so you see it. I'm looking at the alpha only if beta up there.
Oh, you're cheating. Make an appeal to your intuition. Yes, this is the antecedent,
Yeah.
and this is the conclusion. So it's if it will rain tomorrow, then it got cold. If it will rain tomorrow, then it gets cold. Sounds weird. Then it will get cold.
but where does that only go?
It's not in there anymore. So alpha only if beta is the same thing as if alpha then beta. Now, hopefully, if you were thinking about it, you're probably still a little confused by this one and feel like it doesn't quite jive right with you, right?
Yeah, a little.
So here's the example that I found, brings it home for the kids. So we'll look at this one. There is oxygen if there is fire, says what?
If there's oxygen, then there's fire.
If there's fire.
There is oxygen if there is fire, says, put it in the if-then for me.
If there's fire, then there's oxygen.
If there's fire, then there's oxygen. You know that you need oxygen to have a fire, right?
Yeah.
So if there's fire, then there's for sure oxygen, right? There is oxygen if there is fire. You see how that and that are saying the same thing?
Yep.
Now let's read this one. There is fire only if there is oxygen. Is that true?
Yeah.
Yes.
There is fire only if there's oxygen. So you see how that's saying the same thing as if there's fire, then there's oxygen?
Yeah.
So that and that and that are all saying the same thing.
Yeah.
So notice this one is of the form beta if alpha. That's this one, right? And this one is of the form alpha only if beta. You see that? So when plugging in that only word, flips it. As strange as that seems to our intuition. And this example seems to help kids help it click in their heads. That one click? Okay. I'm going to leave those two up there, that these say the exact same thing. Maybe put it one more way. These are both saying alpha implies beta, right? Okay. Because that's going to be an important connection for us to make here in a sec. Okay. So we did a bunch of examples converting those. Okay. Now, a little bit of exercise doing proofs. Here's what I want you to do. I want you to assume that this is true. Sorry. What can you conclude given the following statements? So assume that this is true, and then tell me what else is true if A is true, and then tell me what else is true if instead B is true. You with me?
Mm-hmm.
So we're going to start out in the universe. If Fred is on the team, he must go to bed early. We're in a universe where this is true. You with me?
Yeah.
Okay. What happens if you know? So what do you know if Fred goes to bed early? What do you know?
He's on.
Can you conclude that?
No.
If you know that if Fred is on the team, he must go to bed early,
Oh, yeah.
and you know that Fred goes to bed early, what do you know? Do you know that he's on the team? No, he might not make the team, and he might just go to bed early because he's feeling a little depressed. He didn't make the team. You know? All right, next one. So now assume if Fred is on the team, he must go to bed early. And let's say Fred does not go to bed early. What do you know?
He's not on the team.
He didn't make the team. Right?
Mm-hmm.
Because if you make the team, he has to go to bed early. But he didn't make the team.
Yeah.
But he didn't go to bed early, so we know he didn't make the team.
Yeah.
Perfect. This is the type of reasoning you need to do when you're constructing proofs. Let's do it again. If a man is a postman, he has foot trouble. Okay? So now let's say this man has perfect feet. What do you know?
He's not a postman.
He's not a postman. Okay. You come across some other man. That man has foot trouble. What do you know?
We don't know.
You don't know anything except for that he has foot trouble. He may or may not be a postman. It's still possible he's a postman, but you don't know. Okay, next. You will be given a ticket only if you are a sophomore. Jean was given a ticket. What do we know?
She's a sophomore.
Okay. George is a sophomore. Does he get a ticket?
Yeah. Oh.
No.
No.
No. The only if will get you. Remember, only if is the same thing as implies. If it's alpha only if beta, that's the same thing as alpha implies beta. So you will be given a ticket implies you are a sophomore. If we know George is a sophomore, we know nothing about whether or not he gets a ticket. We just know he's a sophomore. So they're only giving tickets to sophomores. That doesn't mean every sophomore gets a ticket. Good? All right, next one. The house will burn down if we don't get water. All right, let's say we did get some water. What can you conclude?
It still could have burned down.
It still could have burned down, right? The house is burning. You run and you go get a little bucket of water. Did that fix the problem?
No.
No. Okay. B. We didn't get some water.
The house burned down.
The house for sure burns down if you didn't get water. Just because you got water doesn't mean it didn't burn down. But if you don't get water, it for sure burns down.
Oh, the house is currently on fire.
Yes.
I thought that was the house going to be on fire. Okay.
The house will burn down if we don't get water. Yeah, I picture that as a currently burning house. But once again, has nothing to do with the actual facts of reality. It's just the logic of it. I can replace house with dough. The dough will caw. I can make up words for everything that has to do with anything in this universe. And you can still determine what we can know. Okay. Good, good, good. Okay, so now finally, let's try and do the truth table for this beast. Alpha implies beta. Hint. If a statement is not false, what is it? True. True. Okay. So keep that in the back of your mind as you try to fill out this truth table. All right. So we're going to do alpha implies beta. So I need an alpha and a beta. And then we're going to do alpha implies beta. With me?
Yeah.
We have 4 cases still. True, true. True, false. False, true. False, false. This one definitely helps when you see it. Alpha is Donnie's holding a red marker. Beta is Donnie's holding a purple marker. With me? Okay, so the first scenario. Is it true that if I'm holding a red marker, I'm holding a purple marker?
Why would that matter?
Okay,
Wait,
so
you
the
said
first
and
place
then?
that people get stuck. He's over there thinking, I could drop the purple marker at any time, right? So you're trying to apply physics to the scenario. Pretend that me holding these markers is all of existence. There is no physics. There is no universe. There's no you. There's no nothing else. It's just me and these two markers. There's no such thing as motion, change, time. There's no physics. This is existence. You with me? Okay, let's try it again. If Donnie's holding a red marker, then he's holding a purple marker.
Okay, yeah, it's true.
True.
Why does the red mark do anything with the purple?
Because if he's holding a red marker,
If,
then he's holding.
look at this scenario. This is existence, as you know it. Is it true that every time I'm holding a red marker, I'm holding a purple marker? If this is existence forever, nothing changes.
With that universe.
We're going outside the universe. We're no longer talking about physics.
Yes, with that universe. then
Yes.
there's-
Yes. In that scenario, if that's the state of the world, that statement is always true that Donnie's holding a red marker, and the statement Donnie's holding a purple marker is always true. Is it true that if I'm holding a red marker, I'm holding a purple marker?
But how does the red imply that you're holding purple?
There is no causal connection.
Then why does the word implies good work effective? Why does it fit? How would you? Implies does not make sense there.
You are trying to limit implies to something causal in our universe. Mathematics and logic has nothing to do with our universe. Okay, so we are setting up this case. A case where this is always true and this is always true. So you now exist in some universe, some reality, some hyper-reality, whatever you want to call it, where it is always the case that Donnie's holding a red marker and Donnie's holding a purple marker. Do you then know, always on forever, if Donnie's holding a red marker, he's holding a purple marker?
Yeah.
And if you're getting stuck on is it true, ask yourself this question. Is it false? If it's not false, what is it?
True.
By definition, not false equals
True.
true. So this one is true. Let's try the next one. If Donnie's holding a red marker, then he's holding a purple marker.
False.
False. If Donnie's holding a red marker, then he's holding a purple marker.
Yeah.
Is it true? That's hard to think about. Is it false? Is it false that if I'm holding a red marker, then I'm holding a purple marker?
Yes.
That's false?
No, that's.
That's not appealing to your intuition like I hoped.
You're not holding a red marker, but you're still holding a purple.
Yes.
If I'm holding a red marker, then I'm holding a purple.
What?
Is it true?
Can't you hold a purple without holding red though?
This is the universe in existence forever. Me like this.
But that's
Nothing changes. No physics.
false.
This is existence. Is it true that if I'm holding a red, I'm holding a purple? If that hurts your intuition, think about it this way. Is it false that if I'm holding a red, I'm holding a purple? Is that false? No. So if it's not false, what is it?
True.
True. And we call that vacuously true. Vacuously true means you can't check the antecedent. Right? So let me give you another example of a statement. If Donnie is a 20-foot purple dragon, the sun is made of marshmallows. True or false?
True.
True. It's vacuously true. Donnie is not. I don't even remember what I said. A giant purple dragon. So that's what we call a vacuously true statement. All right, let's see if you get the final one. If Donnie's holding a red marker, then he's holding a purple marker.
False. True.
Vacuously true. There's no cases to check. If the antecedent is false, the implication is automatically true. And notice that the scenario I just gave you before was a scenario where they were both false. I said if Donnie is a 20-foot purple dragon, the sun is made of marshmallows. Both those statements were false, their implication is true. Now, implications in mathematics, the ones we're interested in, are going to be like this or like this for the most part. We don't really work that much with vacuously true statements. But there are vacuously true statements. Good? Okay. Vacuously true. An implication is vacuously true provided that the antecedent cannot be satisfied. If it's impossible to satisfy the antecedent, it's vacuously true. Hopefully that makes sense now. Okay, converse. The converse of alpha implies beta is beta implies alpha. Pretty straightforward?
Yeah.
Okay. So let's state the converse of some statements, see if you got it. State the converse of the following implications and determine if it's true. Okay, So let's start by saying if the initial statement is true, then talk about its converse. So if an animal is a man, then it is a human being. Is that true?
Yeah.
If an animal is a man, then it's a human being. That's true, right?
Yeah.
Okay, what's the converse of that?
If an animal is a human being, then it is a man.
Perfect. That's the converse. Is the converse true?
No.
If an animal is a human being, then it's a man? No, it could be a woman. Right? So notice that the converse of an implication is not the same as the initial implication. Alpha implies beta is something very different from beta implies alpha. They're very different statements. Okay. Every man born in Indiana is an American citizen. Is that true? Yeah. What's the converse of that?
Every American citizen is born in Indiana.
Is that true?
No.
No. Perfect. Next one. If x minus y equals 3, then x is greater than y. Is that true?
Yeah.
Yeah.
Yes, yes.
When you take x, if you subtract a bunch of stuff from it, you're still 3. Then what you subtract away must not have been bigger than x. There were still leftovers when you took away y.
Well, unless x was a negative.
No, because then y has to be more negative. Because if x is negative 3, then y has to be negative 6.
Yeah.
So x is still greater than y. Okay, so if x minus y equals 3, then x is greater than y. Okay, what's the converse of that? You're not doing negation or anything like that.
If
You're just switching the antecedent and conclusion.
If x is greater than y, then x minus y equals 3.
Perfect. That's the converse. And is the converse true? No. Okay, next one. If plants are green, they must have sunshine. Is that true?
yes.
Yeah.
Yes. All plants must have sunshine.
Yes.
And so the green ones, they need it too. So if plants are green, they must have sunshine. What's the converse of that?
If
Plants have sunshine, they must be green.
Perfect. And that is it true or false?
It's true.
False.
False.
Oh, yeah.
Right? There's plants that aren't green.
Oh, yeah.
Okay. If 2 plus 4 equals 5, then 4 plus 7 equals 10.
If 4 plus 7 equals 10, then 2 plus 4 equals 5.
Well, first off, is the initial statement true?
No.
No. Okay. And then you said it's converse. The converse is, well, hold on. Sorry. I went too fast. If 2 plus 4 equals 5, then 4 plus 7 equals 10. Is this true? Is this part true or false?
False.
Oh, the implication.
Is this part true or false?
False.
False. So it is 100% true that every single time 2 plus 4 equals 5, 4 plus 7 equals 10.
Oh.
That's 100% true.
Vacuous.
Because this is never the case. Vacuously true. Okay. So, if 2 plus 4 equals 5, then 4 plus 7 equals 10 is
True.
true. Teaching you math here, right? Okay, now what's the converse?
If 4 plus 7 equals 10, then 2 plus 4 equals 5.
And that one's obviously false, right?
Oh, that's true.
No, it's true. Good.
I was like, wait, what? No, he disagreed. True.
Okay. Next, we have what we call the contrapositive. The contrapositive of alpha implies beta is not beta implies not alpha. Okay, and that one, it turns out those are identical. Those say the exact same thing. I know, weird, right? So let's add on to our truth table here that we fortunately kept and show that that's the same thing. So our next column here, just extended. we're going to need a not alpha, we're going to need a not beta, and then we're going to need a not beta implies not alpha. Notice that we also changed the order. We changed the order and put a not on both of them.
Yep.
Going from here to here. You see that? Okay. So really quick, looking at this table, start reading me values.
False. False.
True.
True.
True. False. False. True.
Okay. So now here, you're doing this implies this. You with me? So false implies false is
True.
true implies false is
False.
false implies true is
Yeah.
vacuously true. If the antecedent's false, it's true. And true implies true is false.
No, it's true.
Oh, okay. Good correction. All right. So now, look at this column and look at this column. They always spit out the exact same thing.
Wow.
If you always spit out the exact same outputs for the exact same inputs, you're the same. You do the same thing. Okay. So, turns out this is absurdly useful. Sometimes thinking about a statement this way is really hard to think about it, and so thinking about it this way becomes real easy to think about it. And we'll see examples of that. Okay, so that's the contrapositive. And maybe we're doing examples here. Examples. State the converse and contrapositive of each. Let's just do the contrapositive. I think you guys got the converse down pretty good. So, what's the contrapositive of this? X equals 3 implies x squared equals 9.
X squared does not equal 9 implies x squared does not. Or x.
X squared not equal 9 implies x is not equal 3.
Yeah.
Okay, so notice how these are saying the exact same thing. If I know that x equals 3, I know that x squared equals 9. Similarly, if I know that x squared is not equal 9, I know that x is not equal to 3.
Okay.
Good?
Yep.
Notice that this is different from just the converse. What's the converse of this statement?
X squared equals 9 implies x equals 3.
Does this and this say the same thing? If you know that x squared equals 9, do you know that x equals 3?
I don't know.
What do you think, Jeremy? Yes?
Yes, because, wait.
All right, Emma, tell them while they're wrong.
Unless it could be negative.
Because x could also equal negative 3. Negative 3 squared gives you 9. 3 squared gives you 9. So no, the converse does not give you the same thing. The contrapositive gives you the same thing. This and this say the same thing. Good? Okay. Again, just state the contrapositive. If two lines intersect, they are not parallel.
If two lines are not parallel.
No?
Two lines are parallel.
Two lines.
Perfect.
Oh.
If two lines are parallel,
Then two lines do not intersect.
then
Two lines
They don't.
do not.
then they don't intersect. I don't need to write it. You got it. Perfect. Next one. If food is sweet, then it has honey in it.
If food does not have honey in it, then it is not sweet.
Perfect. Next one. If there's no atmosphere on Mars, then there is no life there.
If there's life on Mars, there is an atmosphere.
Perfect. If no atmosphere implies no life, then life implies an atmosphere. Good? Next one. Oxygen is a necessary condition for fire.
Fire is oxygen.
All right, let's start by putting this in an if-then form. So how do we say that one?
If there's fire, there's oxygen.
Perfect. If fire if fire, then oxygen. Right?
So if no oxygen, then no fire.
Perfect. If not oxygen, I'll just say O2. Not oxygen, then not fire. Good?
Yeah.
Perfect. Okay, logical equivalence, or the if with two F's. And we'll explain why it's an if with two F's. Okay, so observe that alpha if beta is the same thing as beta implies alpha, right? Alpha if beta means if you have beta, then you have alpha.
Yes.
Good?
Yeah.
Okay, and that alpha only if beta is the same as alpha implies beta.
Yes.
So alpha if beta does beta implies alpha. Alpha only if beta does alpha implies beta.
Yeah.
Okay, so then if I tell you that we have alpha if and only if beta, then that means we have alpha implies beta and beta implies alpha. Beta implies alpha from the if, alpha implies beta from the only if. You with me?
Yes.
Okay. Now we say in mathematics a lot. Alpha if and only if beta. We say it so frequently and we write it so frequently that we get sick of writing all those words, and so we shorten it to alpha if with two F's beta.
Yeah.
So when you see two F's on there, it means if and only if. Good?
Yes.
Okay, and this is also shorthand for what we mean by logical equivalence. This is our last logical operator. Logical equivalence. We call the two statements, alpha and beta, logically equivalent, provided that alpha implies beta and beta implies alpha. Now, unfortunately, I need a truth table for this. And my chalk is running out again. All the new chalk is garbage, so you have to go find old pieces and get what you can out of it. Okay. So, let's make sure that this one makes sense, and then you'll understand why it's called logical equivalence. Okay, so we're going to be doing an alpha. We're going to be doing a beta, right? We need to know alpha implies beta. We need to know beta implies alpha. And then finally, we need to know alpha if and only if beta. And I don't think I let you see the symbol for that yet, but it's this. Alpha, back and forth arrow, beta. That's if and only if. You with me?
Yeah.
So this is true only where this is true and this is true. This is a conjunction of these two. Good? Okay, so let's write out our cases. We can have true, 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 false, false, true, and false, false, right? Okay, alpha implies beta.
True. True.
True,
False.
false,
True.
true,
True.
true. Good. Next one, beta implies alpha.
True.
False, right?
Yeah.
No, true.
True.
Antecedent's false. True implies false is,
False.
and then false implies false is.
True.
Okay, so now, where do we have alpha and alpha implies beta and beta implies alpha?
True.
So we're adding together these two columns.
True. False. False. True.
Now notice that this column is only true when alpha and beta have the same value.
Yeah.
Here they have the same value, here they have the same value.
Yeah.
So logically equivalent just means you have the same value. Logically equivalent, same value. That's all it means. Make sense? Okay. So that is our last logical operator. So give you a recap of all the operators that we talked about. We talked about not, we talked about and, we talked about or, we talked about implies, and we talked about if and only if or logical equivalence. Right? Okay. So those are the 5 big operators. You can come up with other operators like the exclusive or NAND, or there's a bunch, but These are the ones that we typically use. Okay, we did that. Logical equivalence, we defined that. Notation, back and forth arrow. Precedence, or order of operations. You inherently know that if I see -3 times 2 plus 7, you know that first you apply the negative to 3.
By parentheses.
Huh?
Yes.
Without adding parentheses. I'm saying when we ignore the parentheses, here's what's understood. First you apply the negative to the 3.
Yes.
Then you take the 3 and you multiply it by 2.
Yes.
And then you add the 7. So you apply the negative first, then you do negative as in, not the same thing as takeaway, just negative. So I'll do neg to specify. We do negative, and then we do plus or minus, those are really the same thing. And then you finally do multiplication or division, those are really the same thing. And that's the order that you do it in. That's the order of precedence. You do this, and then this, and then this, etc., right? What if I had an exponent here? So what if I did -3 squared? Do I do the negative first or the exponent first? The exponent. That's -9. So we do exponents first. exp for exponents. Order that we do these operations in. Or precedence. This takes precedence over this, takes precedence over this, takes precedence over this. In logic, here's our order of precedence. Not, and, or implies logically equivalent. This one functions a lot like the equal, and the equal is the last thing you focus on, right? When I do this is equal to, well, let's figure out what we get really quick. 3 squared is 9. 9 negative, so -9 times 2 is -18, plus 7 is -11. So we'll say 2 minus 13, right? Same thing? You with me? We don't say, oh, this statement is saying that 7 equals 2. We apply the equals after everything else, right?
Yeah.
Kind of. Equals isn't really an operator, but just think about, we think about that the same way we think about equals. It's what comes very last. Okay, so I'll give you a quick example. If I tell you alpha implies beta is logically equivalent to not beta implies not alpha, you probably already think about that correctly. We're saying that this, with parentheses, is the same thing as this with parentheses, right? And you probably already knew, you do the not beta before you do the implies, and you do the not alpha before you do the implies. That's what we're saying. You do the not first, then implies, then logical equivalence. And I rewrote it out over there. Same thing. Similarly, this one might have been a little bit more confusing, so here's one that you just kind of have to memorize. If I did alpha or beta and not alpha, the parentheses go right here. And takes precedence over or, the same way that multiplication takes precedence over addition. And acts like multiplication for logic the same way that multiplication acts on numbers. They're very similar operations. And or and plus are very similar operations. Good? Okay. Proofs. Maybe we'll start with proofs next time. So you got the foundations of propositional logic. So next time we'll move on to how we start constructing some basic proofs, give you intuition for basic proofs, and we'll finish up this logic and hopefully start on the axioms next week as well. Hopefully. Jeremy looks like he was getting tired, so we have to call it.